Greetings of the day. In today's lecture, we are going to discuss various techniques. I will give you an introduction to various methods of mitigating the power quality problems. In last few lectures, we have discussed various types of power quality disturbances or power quality issues or power quality phenomena or what you call as power quality problems. And we have also studied causes of these power quality problems and their impact on the customers, on the utility, on the end user. Now, from today, this lecture onwards, we will discuss various methods of improving the power quality in the distribution systems. Now, in today's lecture, I will give you introduction to a group of devices which are used for improvement of power quality, and those devices are called custom power devices. So we are going to discuss custom power devices, CPDs. CPDs means custom power devices. In this lecture, I am going to give you an overview of various types of custom power devices which are under research, which are being researched for improvement of various types of power quality problems. Now, first of all, you have to understand the term custom power. Custom power, CP. See, this term is analogous to the term flexible AC transmission system. Flexible AC transmission system, that is FACTS. See, FACTS is a technology which is used on the transmission side, and custom power is a technology which is used on the distribution side. Both these technologies use or make use of power electronic devices, power electronic converters. FACTS is a term that pertains to use of power electronic devices in the transmission network, on the transmission side. On the other hand, custom power is a term that pertains to the use of power electronic devices on the distribution side. That is the difference between the two. Both these techniques or both these technologies use power electronic devices, but FACTS uses these power electronic devices on the transmission side, and custom power technology uses the power electronic devices on the distribution side. Now, just like FACTS improves the reliability and quality of transmission by way of enhancing the power transfer capability and stability of the system, custom power also enhances or improves the reliability and quality of power supply to the customer in a distribution system. I hope since you are already studying this flexible AC transmission systems, FACTS, in this FACTS you will see that the various types of FACTS devices, which are shunt connected devices, series connected devices, and combined shunt and series connected devices, they actually, what they do, they improve the performance of transmission line. They increase the power transfer capability of an existing transmission line so that the same line can transfer or transmit more amount of power. They also improve the stability of the transmission system, and hence they result in a better and reliable transmission network. Similarly, analogously, or on the other hand, these custom power devices, they use power electronic devices. They also use shunt controllers, series controllers, or a combination of shunt and series controllers, which are based on power electronic devices, and they improve the performance of the distribution system. They improve the reliability and quality of power supply which is being delivered to the consumers or to the customers in the distribution system. Okay, so these two terms are synonymous to each other. The only difference being that FACTS is used on the transmission side to improve the reliability and quality of the transmission network, and CP, custom power, is used on the distribution side to improve the reliability and quality of power supply to the customers. So therefore, what is custom power? How do you define the custom power? Let us define custom power. I will define it as custom power is a term that pertains to the use of power electronic devices or power electronic converters, power electronics devices in the distribution system. To improve the reliability and quality of power delivered to the customers or consumers. Okay, so it's a term that pertains to the use of power electronics devices or power electronics converters in the distribution system. Why do we use these power electronic devices in the distribution system? To improve the reliability and quality of power which is being delivered to the consumers or to the customers. Now, how do these power electronic devices improve the reliability and quality of supply? During short interruptions, they ensure, some of these power electronic devices, they ensure that power supply to the load is not disrupted, even during short interruptions. They take care of various power quality problems like voltage sags, voltage swells, voltage harmonics, voltage flicker, current harmonics, okay, then three-phase unbalance, phase unbalance, magnitude unbalance, and reactive power. So whatever type of power quality issues or power quality problems we have been discussing over the last 3 to 4 lectures, these power electronic devices which are used in custom power technology, they take care of all these types of power quality problems, and they ensure a reliable and high quality of power delivered to the customers. Now, this is about custom power. Therefore, custom power is a term, or it is a technology that uses power electronics devices in the distribution system to improve the reliability and quality of power delivered to the consumers. What are custom power devices then? Custom power devices are these power electronic devices which are used for this purpose. So custom power devices are the power electronics devices or power electronics converters which are used in the distribution system to improve the reliability and quality of power delivered to the customers or consumers. Custom power is a technology, and custom power devices are the devices which are used in this technology for this purpose, for improving the reliability and quality of power supply delivered to the customers. So I hope that's clear. Now, this custom power devices are not very old. I mean, it's a new technology. It's still in its infancy, and a lot of research is going on in custom power devices for improving their performance, for improving their efficiency, for the mitigation of various types of power quality problems in a better way. Okay, and industries as well as academia both are working in this area for design and development of various algorithms for better operation of custom power devices to address various types of power quality problems. Now, as far as these custom power devices are concerned, or as far as this custom power is concerned, these custom power devices are of mainly 3 types. They are shunt type. Shunt type means the devices connected in parallel with the distribution network, or some of them are of series type, which are connected in series with the distribution system, and some of them are combination of shunt and series. Combination of shunt and series. Another category of these custom power devices is based on current breaking. I mean, there is another class of custom power devices which break the current whenever required. Current breaking, current limiting, and current transfer. So we will see, we will study the classification of custom power devices later on. Now, in order to understand the use of custom power devices, we have to understand the interface between customer and utility. Let us try to understand that. Interface between utility and customer, or I should write it like this: utility customer interface. To understand the interface or interaction between utility and customer, let me draw a single line diagram of a distribution system. This is the source. This is a load bus here. Let us call this bus as bus 1. This is feeder. This is bus number 2. Load bus again. This is another feeder. And this is another bus, bus 3. You have certain loads connected to bus 1. So load, it may be a single load, or generally it is a combination of many loads. You have loads connected to bus 2 also. So load, and you have loads connected to bus 3 also. Load. So this is the single line diagram of a radial distribution system, which comprises of a source, and this source is feeding 3 load buses. What are the 3 load buses? Bus 1, bus 2, and bus 3. And these 3 load buses are connected by 2 feeders, feeder 1 and feeder 2. Now all the 3 load buses are supplying power to the loads. So there is a group of loads connected to bus 1. There is a group of loads which is being fed from bus 2, and there is a group of loads which is being fed from bus 3. Okay. Now you will study in future classes that whenever there is an unbalance in a 3-phase, this is a 3-phase system, and I have shown the single line diagram. Actually, it is a 3-phase system. Now in this, you will have single phase loads as well as 3-phase loads, and 3-phase loads will be mostly motor loads. Now it is possible that some of the loads or some of the 3-phase loads are unbalanced, or the 3-phase loads and single phase loads which are used on a particular bus, they may cause unbalance in the system. So whenever there is 3-phase unbalance, whenever there is 3-phase unbalance, now this 3-phase unbalance in the load means that load draws the currents, say line current IA, line current IB, and line current IC, which are not balanced. I have already told you what do you mean by balanced 3-phase system. A 3-phase system is said to be a balanced system if the magnitude or amplitude of all the 3 line or phase currents is same. The phase relationship between consecutive line currents is also equal. I mean, current IB should be lagging behind current IA by 120 degrees. IC should lag behind IB by 120 degrees, and IC should lag IA by 240 degrees. So such a system is called a balanced 3-phase system. But your 3-phase system may not always be balanced. There are many reasons that a 3-phase system becomes unbalanced. Maybe single phase loads on a 3-phase 4-wire system makes the system unbalanced. And when the system is unbalanced, the magnitude or the amplitude of the 3 currents is not same. So IA is not equal to IB, not equal to IC. So such a system is three-phase unbalanced system, or there may be unbalance in the phase angles also. Now, because of unbalanced currents drawn by a three-phase system, what will happen? The voltage drops in these feeders will also become unbalanced, and therefore voltages which are available at the three buses, say VB3 is the bus voltage 3, VBT2 is the voltage at bus 2, and VB1 is the voltage at bus 1. So these three-phase voltages, because of unbalanced currents, will also become unbalanced. And because of unbalanced three-phase voltages, there will be problems in many equipments operating, I mean three-phase equipments which are designed to operate satisfactorily when fed from a three-phase balanced system. When they get unbalanced voltages, they will not perform satisfactorily. For example, if a three-phase unbalanced voltage is fed to a three-phase induction motor, the induction motor will excessively heat up. There will be large heating, reduction in the efficiency, rise in the temperature, and to keep the heating or temperature of the motor within control, within the permissible limits, you may have to derate the motor. So therefore, three-phase unbalance will result in three-phase unbalance means unbalanced currents will result in unbalanced three-phase voltages. Okay, so it is possible that some of these loads may cause unbalance in the currents, and hence the voltages at various buses will also become unbalanced. Now there may be some loads on these buses. In addition to unbalance, there may be some loads which are operating in these buses which are drawing distorted currents, distorting loads, distorting or non-linear loads. I have already given you an example of various types of non-linear loads. All power electronics based loads which use front-end AC to DC converters, they act as non-linear loads. Now it is possible that the group of loads in load on bus 3, it has non-linear loads, or any of these buses they are feeding non-linear loads. Now these non-linear loads draw distorted currents from the supply, distorted currents which are rich in harmonics. And you already know when these distorted currents flow through the feeders, like feeder current IF1 will be distorted, feeder current IF2 will also be distorted. The distorted currents will result in voltage drops, and hence the voltages at point of common couplings. These buses are points of common couplings. Voltage VB3 will also get distorted. Because of distortion in the line currents or feeder currents, the bus voltages will also get distorted. I mean, this source voltage is purely sinusoidal, this Vs is purely sinusoidal, but because of nonlinear loads somewhere here, the feeder currents get distorted, and hence voltages which are available at the buses VB1, VB2, VB3, they will also get distorted. So therefore, three-phase unbalance results in unbalanced voltages, and nonlinear loads result in distorted currents. It is also possible that some of these loads are operating at a very poor power factor. That is another power quality issue. Maybe some loads are operating at poor power factor. Maybe some loads connected to bus 3, they are reactive loads, inductive type loads, and they draw the currents at very poor power factor. So since power factor is very low, low power factor means they draw large reactive power. In addition to active power, they draw large amount of reactive power. And large amount of reactive power will increase the feeder currents. Because what type of currents are flowing on the feeders? It is not only the active component of current which is flowing, it is the reactive component of current also which is flowing. And because of deterioration or because of poor power factor of some of the loads, say at bus 3, the reactive power drawn by some loads at bus 3 is very large. So that means these buses, in addition to active power, they are carrying large amount of reactive power also. So that will increase the feeder currents, and because of increase in the feeder currents, there will be more I square R losses in the feeders, because these feeders are having some resistances, and since the magnitude of current increases because of large reactive power, I square R losses, that is power losses in the feeders, will be high. So this I square R loss will increase, and I into X, that is voltage drop in these feeders, will also increase, because since I increases due to increase in reactive power, so voltage drop VD, which is equal to I into X, will increase. So therefore voltages at these buses VB2, VB3 will be less than specified voltages. Okay, so there will be large voltage drops. So therefore, three types of power quality problems can occur there, which are based on the loads. And all the three types of power quality problems are caused by the type of loads. First is three-phase unbalance. The three-phase currents are unbalanced, which will cause unbalanced voltages at these buses. Second is nonlinear loads. Maybe at bus 3 you have some nonlinear loads. They will draw distorted currents which are rich in harmonics, and the voltages at these buses will also get distorted. And third is that some of the loads which are connected at some bus, say bus number 3, they draw the power at poor power factor, hence they demand large reactive power. Because of large reactive power flow, the feeder currents will increase. That will increase the copper losses or power losses in the feeders, and that will also increase the voltage drops. So because of increase in power losses, the efficiency will decrease. There will be loss in the power in the feeders, and bus voltages will also reduce, and it will affect the voltage regulation of the buses, bus voltages. Okay, so these are the problems which are caused by the loads. In addition to this, let us suppose that at some bus, maybe bus number 1, bus number 2, or bus number 3, electric arc furnace is used. Electric arc furnace. And you already know, I have already discussed with you that electric arc furnaces are responsible for interharmonics, and they are also responsible for voltage flickers. Voltage flickers. They cause voltage fluctuations, and fluctuations in the voltage cause varying changes in the light flicker of the lamp. So that is called voltage flickers. And therefore voltage flickers, if the electric arc furnace is used at bus number 3, one of the loads may be electric arc furnace, so it will result in voltage fluctuations, and therefore voltage flickers will disturb all other loads which are fed from the same bus. So this is another type of problem which is again because of the load. This problem is also created by the nature of the load on one of these load buses. Therefore, what is to be done? Let us assume this bus load or a group of loads at bus number 3 creates all these types of problems. Let us assume that loads at bus 1 and bus 2, they are linear loads. They don't create any power quality problem. But load at bus number 3, let us suppose they are industrial loads, large industrial loads. And large industrial loads are generally non-linear loads. And let us suppose that's a group of loads which is connected to bus number 3. It results in three-phase unbalance and hence unbalanced bus voltages. These loads also draw distorted currents, and hence they result in distorted bus voltages. And let us suppose they also draw, some of these industrial loads draw power at poor power factor, and hence they result in I square R loss, large I square R loss, and voltage drop, and hence voltage regulation of these bus voltages becomes poor. Okay, so therefore these polluting loads which are connected to bus number 3, they have to correct their loads. I mean, some correction measures have to be taken by them, because it is not when these loads distort the bus voltages, when these loads result in unbalanced bus voltages, and when these loads result in large I square R losses and drops in the bus voltages, they are not disturbing their loads connected to bus 3, but they are disturbing loads connected to other two buses also, bus 1 as well as bus 2. Bus 2 will be very severely affected. Bus 1 will not be very severely affected because bus number 1 is connected very close to the source, and the reactance between the source and bus number 1 is very, very small. So this bus number 1 is not going to get affected that much, but loads at bus number 2 will get severely affected, in addition to loads at bus number 3, other loads at bus number 3. So what type of voltage the loads at bus number 3 and bus number 2 will receive? They will receive unbalanced three-phase voltages, they will receive distorted three-phase voltages, and they will also receive low voltages, because there will be large voltage drops across these feeders. So they will receive less than pre-specified voltages. So therefore, it is whose responsibility is this to ensure a good quality of the power? Okay, it is the responsibility of the polluting load, the customer itself, because customer's load is causing all these problems. So what electric utility does? Electric utility issues a notice to the industrial loads which are connected to bus number 3, and they ask them to use the compensating devices, which will take care of three-phase unbalance, which will take care of harmonics, and which will also take care of poor power factor. They will improve the power factor. Now we know how to improve the power factor. The simplest way of improving the power factor across a load, if this is the load, is to connect a capacitor bank across this load. And how to take care of the harmonics. If this load is a nonlinear load, it is drawing harmonic rich currents. The passive LC filters, passive harmonic filters can be designed. Passive harmonic filters, which are basically LC filters, they can be connected across these loads. Let us suppose there is a strong fifth harmonic component. So we design a passive LC filter which traps this fifth harmonic current I5. You have to arrest the seventh harmonic current also. For that you have another single tuned filter which traps seventh harmonic current. You have to trap 11th harmonic current also. So you design another filter, single tuned filter, which traps 11th harmonic current, and hence no harmonic currents will flow in the lines, in the feeders, because all these harmonics will be trapped by these filters. There may be 13th harmonic filter also. I have not shown that. There may be other filters also. So therefore, this is the simplest way of, this is how utilities were doing it, how load power factor was improved, and this is how the harmonics in the load were arrested conventionally. But nowadays, using custom power device, we have a single custom power device which performs all these activities. We have a single shunt connected device, shunt connected custom power device, which is used in current control mode. Current control mode. And it's a power electronic based device, custom power device. It takes care of all these problems. Load 3, some of the loads at bus number 3, they cause unbalanced currents. So this single custom power device, which is a shunt connected device, I am going to discuss that in a minute's time. It's used in current control mode. It will take care of all unbalance. I mean, if the load draws unbalanced currents, so these feeder currents are also unbalanced. So it will compensate for unbalance in the load currents so that these feeder currents become balanced. Simultaneously, this custom power device will also take care of harmonics. Whatever harmonics are demanded by the load, those harmonics are not drawn from the source. Those harmonics are compensated by this custom power device itself, so that these currents are purely sinusoidal. Feeder currents IF1 and IF2, they are not containing any harmonics. They are harmonic free currents. And what is the third problem? Third problem is that the loads at bus number 3, they are operating at very poor power factor. So this custom power device will take care of power factor also. It will improve the power factor so that this voltage, source voltage or bus voltage, Vs, and current, they are in phase. Is or feeder currents, they are in phase, and hence it will result in unity power factor. That means there will be no flow of reactive power from source to the load. The reactive power compensation will be done by this custom power device itself. So it will take care of all three types of power quality problems. It will improve the power factor of the load to unity, and hence no reactive power will flow. And when there is no reactive power flow, I square R loss will decrease, and I into X voltage drops will also decrease. So these bus voltages, their voltage regulation will improve, and the system will operate at very high efficiency because of copper losses having been reduced. This custom power device will also cause balanced three-phase currents. It will take care of load unbalance, and hence these currents in the feeders, they will be balanced. So these voltages, bus voltages, VB1, VB2 and VB3, they will remain balanced in nature. Now this custom power device will take care of third power quality problem also, that is harmonics. The load current is drawing a large number of harmonics. Earlier those harmonics were being supplied by the source, and these harmonics were flowing all the way through these feeders, causing harmonic voltage drops and hence distorted voltages VB1, VB2 and VB3. But now these harmonics will not come from source. Harmonics will be compensated by this custom power device itself. It will take care of harmonics also, so that no harmonic component comes from source, and these feeder currents or line currents are purely sinusoidal in nature. And hence these bus voltages are also sinusoidal. So their voltage flicker can also be taken care of by this custom power device. But if it has to take care of voltage flickers, it has to then in that case operate in voltage control mode. The shunt connected device has two modes, current control mode and voltage control mode. For taking care of unbalanced three-phase currents, for taking care of harmonics, and for improving the power factor of the system, this shunt connected custom power device operates in current control mode. And for taking care of voltage flickers, because of electric arc furnace, which may be one of the loads here, it operates at that time in voltage control mode. So therefore, this custom power device, it is the responsibility, whose responsibility is this to connect the custom power device across this load? It is the responsibility of the polluting loads. Then electric utility, they ask the consumers, the customers of polluting loads to install this shunt connected device or custom power device across their loads, so that all these power quality problems are issued. But the customers may be reluctant. The customers may refuse to install these shunt connected custom power devices. Why? Because the initial cost of these custom power devices, which this custom power device which has to be connected by the customer across its load, its initial cost may be very high. Initial cost and installation cost. Installation cost may be large, and running cost may also be high. Running cost means it, every year you have to go for maintenance, and in case of any failures of some devices in the custom power device, those devices have to be replaced by new ones. I mean, maintenance costs, running costs. So what customer, because of these heavy costs involved, heavy initial and installation costs and yearly running costs, the customer may refuse to install this compensating device or custom power device across their load. Then what will electric utility do? Electric utility will impose financial penalty on the customer in its tariff, in its electricity bill. Financial penalty. They will ask the customer that you either install this custom power device or this shunt connected compensating device, so that other loads are not disturbed because of your load, polluting load, or you face the financial penalty. The customer opts for it. He says, okay, I am ready to pay the penalty, because paying the penalty is less expensive for him than paying for installation of custom power device. Okay. The problem is that customer every year or every month he pays the penalty, but the issue remains unaddressed. His load continues to draw unbalanced currents, harmonic currents, and poor power factor currents, and it causes problems to other loads which are fed from other buses, including the loads which are fed from this bus also. Now, what is the solution? The other solution or other alternative left with electric utilities is that they will themselves install custom power device across the polluting loads, and they will charge the cost, the installation cost and the running cost from the consumers here. This is another solution. And one more solution with these electric utilities, that since bus number 1 is not very badly affected, being very close to the source, it is bus number 2 which is affected. They may install these custom power device, shunt connected device in voltage control mode across bus 2, where the loads are, mostly the loads at bus number 2 are suffering. This is another alternative. Okay, now these are various alternatives left, and till the customers of polluting loads here at bus number 3, till they get motivated. A time will come when they will get motivated, because they are paying every month, they will be paying penalty, and in the long run it will become more expensive for them to pay monthly penalty than to make one time this investment and installing custom power device. And finally, maybe one fine morning, the customers will come to the utility and they agree to install the compensating device across the load, and then problem will automatically get solved. So therefore, this is how the problem will get solved. This is the utility customer interface. Now, another problem which the loads, industrial loads, which are connected to the bus number 3 will face is the voltage related problems. The problems which I have discussed with you till now, they are current related problems, load related problems. They are the problems created by the polluting loads. The load is drawing distorted currents and causing distorted bus voltages. That was one problem. So that was the problem because of the load current. Another problem was load unbalance. The three-phase load currents here are unbalanced and they cause unbalanced voltages at the buses. That's again load problem. Third problem is that load is operating at low power factor and it is drawing large reactive currents. That is again load problem. And therefore load compensation, the shunt connected compensation device has to be connected by the customers of the polluting loads, which are called custom power devices. Okay, fine. If they agree to install this, all these problems will get solved. But there may be other problems which are voltage related problems. Voltage related problems means that the voltage which is coming from source to various buses, the voltage itself may be distorted. It may be distorted itself. The voltage may not be sinusoidal because of some reasons. And then there may be sags and swells in the voltages. I mean, the voltage may have sag like this, and the voltage may have swell like this. These are voltage related power quality problems. And then there may be voltage flicker also. There may be the voltages which are coming from the source at buses VB1, VB2, VB3. They may be distorted voltages, not because of your load, you have already compensated your load, but they themselves, from the source itself, they may be distorted. And there may be voltage sags and voltage swells. And you already know, if you are using some very sensitive load here, say hospital equipment or a semiconductor manufacturing company is there, a small voltage sag, even of 2 or 3 cycles, will disrupt or disturb the entire manufacturing process and and it will result in huge loss of revenue. So to take care of these voltage related power quality problems like voltage distortion, voltage sags, voltage swells and voltage flickers, the customer may have to connect another type of custom power device, which is not shunt connected, which is series connected custom power device. Series connected CPD, custom power device. So what will this series connected custom power device do? It will take care of problems in the voltage. Like if there is a voltage sag, the voltage, say you want to maintain the bus voltage VB3 constant. because there are some industrial loads, industrial processes where these voltage sags cannot be tolerated. Even if there is voltage sag at bus 1, bus 2, but at bus 3 you have some industrial processes, so you want to maintain bus 3 voltage absolutely constant even if there is a sag in the source voltage. So you connect a series connected custom power device here, and this series connected custom power device will ensure that the voltage sag or voltage swell is not reflected here. Even if there is sag in the voltage, source voltage, swell in the source voltage, but this load voltage is maintained absolutely constant. And even if this source voltage is distorted, the load voltage, the voltage applied to the industrial load, is purely sinusoidal. So it takes care, it compensates the harmonics in the voltage also. So such a custom power device is called series custom power device. And there is another type of custom power device which is a combination of series and shunt connected custom power devices. For example, your load is causing distortion in the currents, it's causing unbalanced voltages, and it is drawing power at poor power factor. And simultaneously, the source voltage is distorting in nature. It is suffering from sags, swells, flickers. So in that case, you need both types of custom power devices. For compensating the load, you need shunt connected custom power device, and for compensating the voltage, you need series type custom power device. Instead of connecting shunt type custom power device separately here and series type custom power device separately here, you have a custom power device available in the market which is a combination of series and shunt connected custom power device. Combination of shunt and series custom power device. It's a combination of both. So the shunt part of this custom power device will compensate for the load, and series part will compensate the load voltages, and hence it will take care of current related power quality problems as well as voltage related power quality problems. I will come to that later on. That is called UPQC, Unified Power Quality Conditioner. I will discuss that later on. Okay, so that is about utility customer interface. So therefore, if some of the loads or groups of loads are polluting type, the only solution to the problem is to install a shunt connected custom power device. If the voltage is polluting type, it has distortions, it has sags, swells, flickers, then series type custom power device has to be connected. And if both problems are there, you need to compensate load as well as you need to compensate the source voltage, then a combination of shunt and series type custom power devices is needed at a particular bus to take care of power quality issues due to the current and power quality issues due to the voltage. So this is about utility customer interface. Now let us discuss the types of custom power devices. Types of CPDs, custom power devices. Now these custom power devices are broadly classified into two categories. One is network configuring type, network configuring type CPDs, custom power devices, and another is compensating type custom power devices. Compensating type CPDs. So these are two broad classifications of custom power devices. Now these network configuring custom power devices are further classified as they result in current breaking, current transfer, etc. And the solid state versions are called solid state current limiting, SSCL, solid state current, solid state breaking type custom power device, that is SSB, and solid state transfer switch. SSTS. These are the three types of network configuring type CPDs. I will come to that. I will discuss them one by one after some time. And compensating type CPDs are first shunt connected custom power device, which is also called distribution static synchronous compensator, DSTATCOM. I'll come to that later on. Second is series type or series connected custom power device, which is called dynamic voltage restorer, DVR. Please bear with me, I will come to that. And third is combination of shunt and series custom power devices, that is called unified power quality conditioner, UPQC. Okay, so this is the classification of custom power devices. I repeat, custom power devices are broadly classified into network configuring type CPDs and compensating type CPDs. Network configuring type CPDs are of three types: solid state current limiting custom power device, that is SSCL, solid state breaking custom power device, SSB, and solid state transfer switch, SSTS type custom power device. And compensating type CPDs are of three types: shunt connected CPD, which is also called DSTATCOM, series connected CPD, which is called DVR, and a combination of shunt and series CPDs, which is called UPQC. And now let us discuss them one by one. First of all, we will discuss the first category, that is network configuring type CPDs. Network configuring type CPDs, custom power devices. Let us discuss first this. Now the first category or first type of network configuring type CPD is solid state current limiter, SSCL. So it is this type. Let me try to explain that. We have a source here. Let me first of all draw the circuit diagram, or SCS, and then this is LM, current through this is IM, and this is feeder current IF, and we have a load connected here. Source, this is load. Now this is switch. This is your, within the dotted line, this is your, this whole assembly is solid state current limiter. Now the voltage across the switch is VSW, switch voltage. Now I am using a bidirectional switch. When this switch, the arrow shows that current in this switch flows in this direction, and arrow this shows that current in this switch flows in this direction. I mean, when there is positive half cycle of source voltage, plus minus, then current has to flow to the load in this direction. At that time, this switch is on and this is off. And when current has to flow in this direction during the, say, for example, negative half cycle of source voltage, the current has to flow in this direction. At that time, this switch is off and this switch is on. So for passing current in this direction, this lower switch is on, upper switch is off. And for passing current in this direction, upper switch is on and lower switch is off. So I hope this is clear. Now what is this LM? LM is current limiting reactor, and the current flowing through this through this current limiting reactor is IM. The feeder current is IF. Now as far as these switches are concerned, they may be simple thyristors, SCRs, like this, connected in anti-parallel. I mean this pair of switches. When this switch is on, I mean when firing pulse is issued to this thyristor SCR, it conducts current in this direction. And at that time, this switch is in the off state because it is reverse biased by the voltage drop across this switch. And when this switch is fired, current flows in this direction, and at that time this switch turns off. Or they may be GTOs. GTO ऐसा symbol होता है. So it is an anti-parallel connected pair of thyristors, or GTOs. So symbolically it is shown like this. This switch is on, current flows in this direction, it is represented by this. And when this switch is on, current flows in this direction, it is that's what I am showing. And what is this RS and CS? It is the snubber circuit. You know, you must have studied in your basic power electronics course, for protecting your devices, SCRs or any other switches, you need snubber circuits, RC snubber circuits. And this is RS, CS, that's RC snubber circuit. Now let us suppose normal current is flowing through the load. Okay, so this switch and this switch is turning on and off. For this direction of current, this switch is on, this switch is off. And for this direction of current, this switch is on, this switch is off. And you know, the current flows at 50 hertz. So the switching frequency of these switches is also 50 hertz. Normal current is flowing. So I can show you this current graphically also to you. Normal current flowing. Feeder current is normal. Now let us suppose there is a fault, say a ground fault or a short circuit has occurred on the feeder or in the load itself. Because of that, a huge current will start flowing through the feeder, and the current magnitude may be so high that the feeder may get damaged, the source may get damaged, or the load itself may get damaged. At that time, what your controller does, it turns off this switch. The switch is turned off. And at that time, when this switch is turned off, this is off, this is also off. So no current will flow through the switch. And at that time, automatically the current will flow through this reactor or inductor. And the magnitude, the value of this inductor is very high. It acts as a current limiting reactor. So therefore, it acts as a current limiting reactor. And it, you know, limits the magnitude of current like this. Feeder current, no doubt this current is greater than normal steady state value, but it does not go to very large values. The current is limited by this reactor till fault is cleared or till your circuit breaker trips. Okay. Now what will happen to the switch voltage? What will be switch voltage? VSW. As long as switch is on, switch is conducting in the first cycle. Previously also it was conducting. When the switch is on, the voltage across the switch is 0, because we already know when a thyristor is conducting, the voltage across it is ideally 0. And when fault occurs and switch is turned off, then it blocks the voltage. When there is voltage across it, it blocks the voltage. And then current flows through the current limiting reactor. And what is the current through current limiting inductor? IM. When there was no fault, no current was flowing through the inductor because the switch was on. And as soon as fault has occurred, switch has turned off and current divert ho gayi, and it is now flowing through the current limiting reactor. Or current limiting reactor mein ye current flow ho rahi hai. Thoda high amplitude ki, but it limits the magnitude of current. As you can see, feeder current is same as this. It limits the magnitude of current. So this is the role of solid state current limiter, SSCL. So the function of solid state current limiter is to take care of short circuits or high fault currents. It limits the magnitude of current. And it is solid. Why it is called solid state? Because it is based on solid state devices, thyristors or GTOs. Okay. So this is first type of network configuring type CPD, that's solid state current limiter, SSCL. Second is solid state breaker. I will not discuss these in details because they have limited applications. That's not our topic of discussion. We have to discuss mainly compensating type these custom power devices. Second is solid state breaker. SSB. So SSB looks like this again. It may comprise of GTOs, more than one GTO in series, that is this, and then a pair of thyristors like this. This is LM and this is IM. And then you may have high voltage protection across these switches. This is high voltage protection and this is your load. This is switch SW1 and this is switch SW2. Under normal circumstances, switch SW1 is conducting and current is flowing like this. For positive hops, for positive current, this upper switch conducts. For negative current, lower switch conducts. At that time, these thyristors are off. And as soon as a fault occurs on this side of the feeder and huge current flows, then these two switches are turned off and these two switches are turned on. And at that time, for some moment, current limiting is there because current flows through this current limiting reactor till the circuit breaker operates. You may have circuit breaker somewhere here. And when circuit breaker operates, all switches are off. Current is, disrupted, it is interrupted. So this is about solid state breaker. And third type of network configuring type, CPD, is solid state transfer switch. Solid state transfer switch. SSTS, or it is also called static transfer switch. Static transfer switch, STS. You can call it SSTS or STS. Means one and the same thing. So it is something like this. Let me first of all draw. This is the sensitive load. I will write here sensitive load or critical load. So here you have two feeders. Let me first of all, what is this? This is solid state transfer switch, SSTS. So this is called preferred feeder. I will write here preferred feeder. And this is another feeder. It's called alternate feeder. Alternate feeder. So actually your load is a sensitive load. It receives power from two feeders. This is one substation. This is another substation. This substation is supplying this feeder and this substation is supplying this feeder. Okay. This is switch SW1 and this is switch SW2. Normally, when there is normal supply, there is no voltage sag, there is no voltage swell, this switch is off. So under normal operation, I will write here, normal operation. Switch SW1 is on and switch SW2 is off. So therefore, preferred feeder supplies power to the load. No power comes from this alternate feeder because this switch is off. So this switch is on, so power is supplied to the sensitive load from this feeder. Now it may happen that there is voltage sag here. As soon as there is voltage sag here on feeder 1, I mean preferred feeder, there may not be voltage sag on alternate feeder. At that time what happens? This switch is turned on first and then power starts coming from this alternate feeder and then this switch is turned off so that no power comes from this feeder. So this takes care of voltage sag or voltage swell. There may be voltage sag on preferred feeder or voltage swell on preferred feeder. As soon as there is a voltage sag on preferred feeder or voltage swell, this switch SWT, I will write here during sag or during swell, SW1 ऑफ हो जाता है एंड SW2 ऑन हो जाता है, बट पहले SW2 ऑन हो जाता है, उसके बाद SW1 ऑफ हो जाता है, सो दैट पावर टू द लोड इज सप्लाइड फ्रॉम दिस ऑल्टरनेट फीडर जिसमें सैग या स्वेल नहीं है, एंड देयरफॉर दिस सेंसिटिव लोड it does not suffer from, it may be an industrial process, manufacturing process, so it is then protected, prevented from voltage sag or voltage swell. But as soon as voltage sag or swell is there on this feeder, preferred feeder, first this is not turned off, first this switch is turned on, so that alternate feeder is on, and then as soon as this switch is turned on and this switch is turned off, this is called make before break, MBB. I mean, you are making this switch before breaking this switch, MBB, make before break. But this is about sag. Now, another scenario may occur that there is a failure of this, there is a fault on this feeder. Say a ground fault or short circuit has occurred on preferred feeder. At that time, power from preferred feeder should not come. Power immediately should come from healthy feeder, which is alternate feeder. But what about switch on or off? So as soon as there is a fault on this feeder, if you use this technique, make before break, I mean you turn on this switch before turning off this switch, so this feeder will also supply power to the short circuit. It will contribute to short circuit current. So therefore, in this case, you have to first of all, as soon as there is a fault on this feeder, you have to turn this switch off. SW1 has to be turned off, and immediately SW2 has to be turned on. That is called break before make, BBM. I mean, this switch is broken before making of this switch. Otherwise, if you go for make before break, I mean यहाँ पे fault हो गया लेकिन आपने ये switch off नहीं किया, आपने ये switch on किया, it will contribute to huge short circuit currents. To avoid that, जो ही यहाँ फॉल्ट आ जाता है, ये स्विच पहले ऑफ किया जाता है, ब्रेक, और ये स्विच मेक किया जाता है, मेक. ओके, सो देयरफॉर दो टाइप की पावर क्वालिटी प्रॉब्लम्स it takes care. I mean, this solid state, this is called, these are the SW1 and SW2, this is called solid state transfer switch or static transfer switch, STS. It takes care of two problems. Number one, voltage sags and voltage swells. If there is a voltage sag or swell on this feeder, it starts supplying power from alternate feeder, which has no voltage sag. और अगर इस feeder में failure हो जाता है, fault आ जाता है, at that time it starts supplying power from this feeder. So it ensures continuous power supply and power supply which takes care of voltage sags and voltage swells. लेकिन इसमें since these switches, when one of the switches turned off, another is turned on, तो इसमें ट्रांजिशन टाइम में थोड़ा टाइम लगता है. इट मे टेक वन साइकिल और मोर देन वन साइकिल और हाफ अ साइकिल टू ट्रांसफर फ्रॉम प्रेफर्ड फीडर टू ऑल्टरनेट फीडर. ओके, सो दिस इज अबाउट सॉलिड स्टेट ट्रांसफर स्विच और स्टैटिक ट्रांसफर स्विच, SSTS or STS. This is how it takes care of these power quality issues. These are network configuring type CPDs. We will not discuss much about these types of custom power devices. We will talk mostly about compensating type custom power devices, जो हमारी दूसरी कैटेगरी है. Second type of custom power devices, that is compensating type custom power devices. Compensating type CPDs, custom power devices. Now these compensating type custom power devices are again of three types. I have already told you. First is shunt connected custom power device, which is also called distribution static synchronous compensator. Distribution static synchronous compensator, that is D-STATCOM. D for distribution, STATCOM for static synchronous compensator. STATCOM is used in FACTS also. You will study in FACTS devices, but the function of STATCOM in transmission systems is different, and its purpose and function in distribution system is different. In distribution system, it takes care of power quality issues like unbalanced loads, neutral currents, poor power factor, voltage flickers, voltage regulation, current harmonics, and so on. The STATCOM, when it is used in FACTS, it has a different purpose there, like reactive power compensation, stability improvement, power transfer capability enhancement, etc., etc. I hope your FACTS teacher will teach you those functions of STATCOM. As far as circuit configuration is concerned, STATCOM, which is used in FACTS, and DSTATCOM, which is used in distribution system. The term D means distribution. It's used in distribution. The power circuit diagram is same. It's basically a three-phase voltage source inverter. Configuration or circuit structure or inverter structure is same, but functions are different. Anyway, I will not go into those details. Let us discuss shunt connected CPD, custom power device, which is called DSTATCOM, or distribution static synchronous compensator. It is something like this. This is your source, the source voltage Vs. We have a distribution transformer, which is of course step down transformer. I have a bus, say bus number 1. To this bus I have a load connected, say load 1. Then this is feeder, and this is another bus, bus number 2, which is point of common coupling, PCC. Okay, the voltage at bus number 2 is Vt, and I have another load connected here, load 2. Now the problem is created by load number 2. Let us suppose load number 2 is a large industrial load, and industrial loads are generally non-linear loads. Let us suppose this load, since it's an industrial load, it's a power electronics based load, it's using front-end AC to DC converter, so it injects currents. This is feeder current or source current IS, so it injects harmonics in the current. Since it is a non-linear load, load 2 is a non-linear load, industrial load, what type of current it is drawing from the source? IS, which is not sinusoidal, which may be distorted, something like this, distorted current, IS. So it is distorting the current. So because of distortion in the current, the voltage at bus 1 and voltage at bus 2 will also get distorted. And therefore, when voltage at point of common coupling, bus 2, gets distorted, the other loads and this load itself will receive a distorted voltage, Vt. Vt may get distorted like this. And if it is a three-phase induction motor, heavy, large three-phase induction motor is used there, then since this induction motor is fed from distorted voltage, Vt is distorted. Because of this distorted current, the performance of induction motor will get deteriorated. It will produce more heating, more losses, less efficiency, cogging, torque pulsations, vibrations, noise, and so on and so forth. We have discussed it in the previous lecture. So therefore, you have to compensate for the distortion in the source current. I mean, you have to provide the compensation for harmonics, so that this current load, so that the load current IL, which is distorted current, it remains distorted. You cannot change it, but the source current becomes purely sinusoidal like this. That is our aim, to make source current in the feeder purely sinusoidal, so that these drops are also sinusoidal, and voltage at point of common coupling, Vt, is also sinusoidal. That's our aim. Second thing is that this load may be a three-phase unbalanced load. Because of unbalance, it will result in unbalanced voltage, three-phase voltage at bus 1 as well as bus 2. And when these unbalanced voltages are applied across the motor, large motors, three-phase motors, which are installed at load number 2, they will produce large heating and poor efficiency. So you may have to derate those motors. So therefore, the compensator which is to be used here, it should take care of unbalance also, load unbalance also. And it should make these line currents purely balanced, so that these voltages are also balanced. Okay, third problem may be that this load is operating at a poor power factor. That means it is drawing large reactive power from the source. Because of large flow of reactive power from the source, I square R losses in the feeders will increase. That will increase the power losses, decrease the efficiency, and also the voltage drops across this feeder, will increase because large current is flowing due to the flow of large reactive power, and therefore voltage at this bus Vt will reduce. It will be less than specified voltage. There will be poor voltage regulation. So therefore you have to overcome these three problems. What you do is that you use a D-STATCOM. D-STATCOM is it provides the load compensation. This D-STATCOM basically provides load compensation. It compensates harmonics in the load. It compensates load unbalance. It compensates reactive power of the load. So therefore it has to be a current controlled. It acts as an ideal current source like this. This is equivalent circuit of it. And it injects a current IF into the system. What is current coming from source? It is IS. What is current flowing in the load? IL. What is current injected by this D-STATCOM? This is your D-STATCOM, which acts as a current source. What is current? It injects into the system. It's a shunt connected device. You can see it's connected in parallel with the load. It's a shunt connected device. But it is in the current control mode. It injects a current IF into the system. And this IF, according to Kirchhoff's current law, IS plus IF is equal to IL. IS, I will write here. IS plus IF is equal to IL. तो आपकी जो लोड करंट है वो है IS plus. यहाँ से अगर आप IS निकालेंगे, I am concerned about IS. I want this source current which is coming from the source. I want it free of pollution. No harmonic should be there. I want it balanced. And I want this voltage, this current in phase with the voltage so that power factor is unity. So the source current IS is IL minus IF. अब ये जो आपका IL है, लोड करंट, जो लोड करंट ड्रा कर रहा है, इसमें बहुत सारी चीज़ें हैं. इसमें डिस्टॉर्शन भी है, I mean हार्मोनिक्स भी है, इसमें अनबैलेंस भी है, और ये करंट वोल्टेज को लैग कर रही है बाय लार्ज फेज एंगल. इसमें I mean पुअर पावर फैक्टर भी है. तो देयरफॉर ये IF आपकी क्या होनी चाहिए? ये इन तीनों चीज़ों को कंपनसेट करना चाहिए. दिस फिल्टर, दिस इज ऑल्सो कॉल्ड फिल्टर करंट और कंपनसेशन करंट. ये जो करंट D-STATCOM इंजेक्ट कर रहा है सिस्टम में, ये हार्मोनिक्स, जो लोड को हार्मोनिक्स चाहिए, जो पहले यहाँ से आ रही थी, ये लोड को सारे हार्मोनिक्स देना चाहिए. सो देयरफॉर इट शुड कंटेन ऑल लोड हार्मोनिक्स, सो दैट आपकी सोर्स करंट जो है वो लोड करंट माइनस लोड करंट में जो हार्मोनिक्स है वो इससे सब्ट्रैक्ट हो जाते हैं और आपकी सोर्स करंट हार्मोनिक फ्री बन जाती है, प्योरली साइनोसॉइडल. ऐसे दिस बिकम्स योर सोर्स करंट 0 to 2 pi and so on. अच्छा, इस लोड करंट में अनबैलेंस भी है. IA, IB, ILA, ILB, ILC बराबर नहीं है. तीन लाइन करंट्स, ILA इज नॉट इक्वल टू ILB, नॉट इक्वल टू ILC. उस वजह से आपकी जो सोर्स करंट है ISA इज नॉट इक्वल टू ISB. I mean थ्री लाइन करंट्स आर नॉट सेम. उस वजह से आपकी बस वोल्टेजेस अनबैलेंस हो जाती है. तो ये फिल्टर करंट इस अनबैलेंस को भी टेक केयर करना चाहिए. I mean ये लोड में जो अनबैलेंस है वो तो रहेगी, लेकिन जो सोर्स से करंट आ रही है ये उसको बैलेंस्ड बनानी चाहिए. दैट इज ISA शुड बी इक्वल टू ISB, शुड बी इक्वल टू ISC. दैट मीन्स इट शुड इंजेक्ट द करंट इन सच ए वे कि ये लोड में जो अनबैलेंस है उसको कंपनसेट करना चाहिए, ताकि सोर्स से जो करंट आ रही है वो प्योरली बैलेंस्ड करंट हो, जिसमें तीनों फेज करंट्स के मैग्नीट्यूड सेम हो. सो देयरफॉर वो इशू भी एड्रेस करेगा. तीसरी प्रॉब्लम ये थी कि जो लोड करंट है ये पुअर पावर फैक्टर पे है, तो उस वजह से सोर्स करंट लैग्स बिहाइंड द सोर्स वोल्टेज बाय अ लार्ज एंगल एंड लार्ज रिएक्टिव पावर फ्लोज. अब इस D-STATCOM का इसका मतलब ये हुआ कि ये जो लोड में जो रिएक्टिव पावर डिमांड है वो कहाँ से आ रही है? दिस सोर्स सप्लाइज द रिएक्टिव पावर डिमांड ऑफ द लोड. और जब सोर्स रिएक्टिव पावर लोड को सप्लाई कर रहा है उस वजह से रिएक्टिव कंपोनेंट ऑफ करंट इस लाइन में फ्लो हो रही है. दैट मीन्स दिस सोर्स करंट कंटेन्स एक्टिव कंपोनेंट एज वेल एज रिएक्टिव कंपोनेंट, जिस वजह से इसका मैग्नीट्यूड बढ़ जाता है, उससे I² और लॉसेस बढ़ती है और वोल्टेज ड्रॉप्स बसेस पे बढ़ती है. I mean this voltage at the bus VT is very less. It is less than specified voltage because large voltage drop across the feeder. अब ये डी स्टैटकॉम जो आपने यहाँ कनेक्ट किया है, ये डी स्टैटकॉम क्या करना चाहिए, जो भी लोड की रिएक्टिव पावर डिमांड है वो यहाँ से आने की बजाय डी स्टैटकॉम को ही सप्लाई करना चाहिए. आई मीन इट शुड सप्लाई the reactive power, Q supply. Whatever is reactive power demanded by the load, it should not come from source. This D statcom should supply this reactive power. So therefore जो filter current है, ये reactive component of current भी contain करेगी और ये इसका reactive power demand भी fulfill करेगी. So therefore this filter current will take care of all the three power quality issues. This filter current will inject the harmonics जो load को चाहिए ताकि यहाँ से harmonics ना आए. It will make line currents balanced. जो भी load की unbalance है, it will take care of that. And it will also supply all the reactive power demand of the load so that no reactive power comes from the source, but reactive power is supplied by D statcom itself. उसकी वजह से जो आपकी source current बन जाएगी, वो एक तो balance बन जाएगी with ISA equal to ISB equal to ISC, जिससे आपकी bus voltages भी balance रहेगी. और ये सोर्स करंट फ्री ऑफ हार्मोनिक्स हो जाएगी बिकॉज ऑल हार्मोनिक्स आर कंपनसेटेड बाय दिस फिल्टर करंट इटसेल्फ. और ये सोर्स करंट इट विल बी इन फेज विद द सोर्स वोल्टेज. अगर आप वोल्टेज देखोगे, दिस इज सोर्स वोल्टेज, यू विल सी सोर्स वोल्टेज, ये source current will be in phase with the voltage. Why? Because all the reactive power demanded by the load is supplied by this D statcom filter current. No reactive power is now coming from the source. So therefore this D statcom supplies it compensates all the three power quality issues. It supplies the reactive power, it compensates the harmonics, and it compensates the phase unbalance in such a way that the source current or line current which is flowing in the line is purely sinusoidal, it is balanced, and it is in phase with the voltage so that power factor is unity. This is how this D statcom works. This is the beauty of this D statcom. It addresses three problems simultaneously. अच्छा, अब अगर यहाँ पे इलेक्ट्रिक आर्क फर्नेस है जिसकी वजह से वोल्टेज फ्लक्चुएशंस हो जाती है, उस केस में यू हैव टू ऑपरेट इट इन द voltage control mode. और voltage control mode में it has to operate like this. I will show it again. This is your source voltage. This is the distribution step down transformer. This is bus 1 and you have some load 1 L1 connected here, and this is feeder. This is source current IS flowing in the feeder. This is bus 2. This is the point of common coupling. और यहाँ पे आपका लोड है लोड 2 which is a distorting load, or maybe it has a single phase electric arc furnace there which causes voltage fluctuations at these buses and it disturbs other loads. So to take care of those voltage fluctuations, we have to use D statcom but in voltage control mode like this, so that it maintains this voltage at the bus absolutely constant, fluctuation free. How do you use D statcom in voltage control mode? We'll come to that later on when we study D statcom in details. और उस केस में इसकी equivalent circuit ऐसी बन जाएगी. Equivalent circuit will be like this. This is the equivalent circuit of D statcom in voltage control mode. Now ये D statcom होता क्या है? ये तो इसकी this is the equivalent circuit of D statcom. We show it as a current source. But how do you structurally, how do you realize this current source? Let me show you how we realize this current source. The actual circuit diagram of D statcom. Let me show you. This is bus 1. This is feeder. And this is feeder current or source current IS. This is load connected to bus 1 or a group of loads. And this is bus 2. This is the voltage at point of common coupling. ये आपका point of common coupling है यहाँ. This is point of common coupling जहाँ पे बहुत सारे loads connected है. A number of loads. Although I am showing only one load, but it is basically a group of loads, which may be combination of polluting loads and non-polluting loads. अब आपका D statcom जो होता है वो ये होता है voltage source inverter. It is a 3-phase voltage source inverter whose symbolic representation is like this. It's shown by an IGBT with a DC bus capacitor CD, and you have a transformer like this, and it injects a filter current IF. This is how you actually realize a D-STATCOM. This is your D-STATCOM, which is a shunt connected compensator, shunt connected custom power device. This is an inverter. You already know the inverter has 3 legs, 2 switches in each leg, total 6 switches, but I am showing only one switch, IGBT with anti-parallel connected diode. Within this box means it's this, it's voltage, 3-phase voltage source inverter, and this 3-phase voltage source inverter acts as a D-STATCOM. It converts this DC into AC, but what it injects into the line is current. And this filter current, this control strategy is such that this filter current or compensating current, which is injected into the point here, it compensates for all types of load power quality problems. It supplies the reactive power demanded by load. It balances the load unbalance. It balances the load currents. I mean, it does not balance load currents, but it compensates the load unbalance so that these source currents are balanced. And it also, compensates for harmonics if there are harmonics in the load. And so that if this is the source voltage, Vs, the source current is also purely sinusoidal, and it is in phase with the voltage, so that there is unity power factor operation. Source current is purely sinusoidal. Voltages at these buses are purely sinusoidal. This is how D-STATCOM is actually realized. In future, those of you who are interested in pursuing their project and dissertation in this field, they can design this D-STATCOM. And a few of my MTech students have already worked on D-STATCOM, and one of my PhD scholars right now this time is working on performance investigation of a D-STATCOM in a distribution system. Those of you who are interested in pursuing their project and dissertation in D-STATCOM, this type of custom power device, they will learn how this D-STATCOM as a current source is realized. So that is about first type of this custom power device, compensating type custom power device, that is shunt connected custom power device, or D-STATCOM. And I have already shown you the equivalently D-STATCOM is nothing but a current source, and how it is realized. It is realized with the help of a 3-phase voltage source inverter. Second type of compensating type custom power devices, series connected custom power device, or it's called dynamic voltage restorer. Dynamic voltage restorer, DVR. So it takes care of, it does not compensate. See, D-STATCOM compensates the load. It compensates for load current harmonics, load unbalance, and load power factor. But series connected CPD, or dynamic voltage restorer, DVR, it takes care of voltage related power quality problems, not load compensation. It does not compensate load, it compensates the source. D-STATCOM takes care of current related power quality problems, but DVR takes care of voltage related power quality problems. What are voltage related power quality problems? Like voltage sag, voltage swell, interruption, short interruptions, harmonics, that is voltage distortion, harmonics in voltage. All these voltage related power quality problems are taken care of by DVR. And this DVR acts as a voltage source. It's like this. I'm again showing same diagram. This is bus 1, where some loads are connected, say load 1. This is the feeder. The current in the feeder is IS, source voltage is VS. This is bus number 2. This is point of common coupling, and you have DVR connected here. The voltage injected in series by DVR is VF, which is also called filter voltage, and you have load connected here. Now you don't need load compensation. आपका load linear load है, it's a balanced load, and it's operating at unity power factor, for example. But there may be problems in the supply voltage, voltage at point of common coupling, VT. It may be a distorted voltage, not because of current distortion. Let us assume current is purely sinusoidal. The distortion in the voltage may be in the source itself. And then there may be voltage sags. You know, some fault on this side upstream has taken place, and that is called voltage dip, voltage swells, harmonics. So all those things will be taken care of by this series connected compensator, which acts as a voltage source. Now what is voltage across the load? It is VL, and current through the load is IL. Now according to Kirchhoff's voltage law, KVL, this VT, that is voltage at point of common coupling, plus VF, that is the voltage injected by the DVR. This is your DVR, series connected compensator, is equal to VL. इससे आपकी VT निकलेगी, VT is equal to VL minus VF. So therefore, जो भी distortions इस voltage में है, source voltage में, harmonics, those harmonics are, यहाँ पे हार्मोनिक डिस्टॉर्शन है, यहाँ पे भी डिस्टॉर्टेड वोल्टेज है, लेकिन आप चाहते हैं कि यहाँ जो आपका लोड है ये सेंसिटिव लोड है, इट शुड गेट purely sinusoidal voltage. Therefore, whatever harmonics are there in the source voltage at this point, at this bus, those harmonics are compensated. This acts as an active power filter. It cancels all the harmonics in the voltage so that the voltage which is available across the load is purely sinusoidal. The voltage VT, this is VT, it may be harmonic voltage, but when it is combined with this filter voltage, the filter voltage cancels the harmonics in the voltage so that आपकी load voltage जो है वो purely sinusoidal बन जाती है. So therefore the DVR compensates for voltage harmonics, and it will take care of voltage dips also. I mean, whenever there is a voltage dip, the voltage में suppose 10% dip होता है, तो यहाँ पे जो आपकी voltage है during that dip it reduces by 10%. तो DVR क्या करेगा, ये इंजेक्ट करेगा उतनी 10% voltage जो इसको ऐड करेगी. So VT जो रिड्यूस हो गई है 10% प्लस VF 10% उतनी मिसिंग वोल्टेज देगा. सो दिस इज से 0.9 प्लस 0.1. व्हाट इज 0.9 प्लस 0.1? 1.0. तो आपकी लोड वोल्टेज को ये मेंटेन करेगा. सो देयरफॉर इट इंजेक्ट्स द मिसिंग वोल्टेज. सिमिलरली अगर यहाँ वोल्टेज स्वेल हुआ, यानी वोल्टेज नॉर्मल से ज्यादा हो गई, इट विल इंजेक्ट अ वोल्टेज विच विल कैंसल द rise in the voltage, and it will always maintain load voltage constant. So this is DVR. DVR it maintains the load voltage always constant and sinusoidal, even in presence of voltage harmonics, voltage sags, and voltage swells. And how do you realize this voltage source DVR? It is realized in practice like this. This is again your source. This is the distribution substation, distribution transformer. This is bus number 1 with some load, say L1. This is feeder with feeder current or source current IS. This is bus number 2. ये point of common coupling है आपका. तो देखिए we realize the DVR like this. DVR should act as a voltage source. It is realized like this. It is also a 3-phase voltage source inverter like this. This is the symbolic representation of a 3-phase voltage source inverter, which has a what is inverter? Inverter has a DC side. It converts DC into AC, and it injects now. Previously we were using it as a D-STATCOM, and in that case it was injecting current. Now here we are using it as a DVR. It injects the voltage through this injection transformer. इसको हम इंजेक्शन या इंटरफेसिंग ट्रांसफॉर्मर कहते हैं. इंजेक्शन ट्रांसफॉर्मर, दिस इज अ स्टेप अप ट्रांसफॉर्मर, क्योंकि ये फीडर हाई वोल्टेज पे हो सकता है और ये इन्वर्टर की आउटपुट वोल्टेज लो वोल्टेज है VF. इसको स्टेप अप करना है टू टेक इट टू द फीडर वोल्टेज. सो यू नीड दिस इंजेक्शन ट्रांसफॉर्मर. और ये आपकी लोड वोल्टेज VL है और यहाँ पे आपका लोड है, load 2. If there is a voltage sag, this injected voltage will take care of that voltage sag and it will keep the voltage at the load absolutely constant. I mean, your VT, this I am writing VT here, voltage at point of common coupling. It may suffer a sag like this. Say 2 cycles तक sag है और फिर नॉर्मल हो जाती है, लेकिन वो लोड वोल्टेज जो है वो कांस्टेंट रहती है बिकॉज दिस filter voltage or voltage injected by DVR compensates this sag. तो it will keep voltage absolutely constant. देखिए sag के दौरान भी ये voltage constant रखेगा क्योंकि जितनी missing voltage है वो that missing voltage will be compensated by this. Similarly, if there is a swell in the voltage, this is VL. Suppose voltage में swell आ जाता है 2 cycles के लिए, फिर वापस आ जाती है. This is VT. तो VL constant रहेगी. सो ये स्वेल आपको लोड वोल्टेज में दिखेगा नहीं क्योंकि जो इसमें इंक्रीज हो रहा है दैट इंक्रीज इज कैंसल्ड बाय दिस इंजेक्टेड वोल्टेज. सिमिलरली इफ द लोड वोल्टेज इज हैविंग हार्मोनिक्स लाइक इट्स हार्मोनिक, लेकिन दिस इज VT, voltage at the point of common coupling, it is very rich in harmonics. So what will this injected voltage of DVR do? It will cancel all the harmonics so that आपकी लोड वोल्टेज VL जो है वो प्योरली साइनसॉइडल हो जाती है. So all voltage related power quality problems will be taken care of by this injected voltage which is injected by this dynamic voltage restorer DVR. So this is the realization of DVR. Third type of compensating power quality, third type of compensating custom power device is a combination of the two. That is called a unified power quality conditioner. I will write here first of all combination or combined series shunt compensator. Or which is called unified power quality conditioner. Unified power quality conditioner. UPQC. It's a combination of it. It may happen that in your system there are both type of power quality problems, current related power quality problems as well as voltage related power quality problems. So it addresses both current related as well as voltage related power quality problems. Voltage related PQ problems, power quality problems. That means you need to compensate load and you need to compensate the voltage also. So you need both. For compensating load, for addressing current related power quality problems, you need D-STATCOM. And for compensating voltage related power quality problems, you need DVR. So the combination, instead of using D-STATCOM and DVR separately, we have one device, one custom power device, which is a combination of series and shunt compensators, which is a combination of D-STATCOM and DVR. That is called Unified Power Quality Conditioner, UPQC. And that UPQC looks like this. I mean, अगर मैं ये VT बस ही आपको directly दिखा दूँ, last portion, it is like this. It comprises of this and this. This is, what is this? By the way, this is shunt compensator और यह आपकी load voltage है VL और यहाँ पे आपका load है जिसको compensate करना. So this is this, it supplies filter current IF. So this is your T-STATCOM. And what is this? This is DVR. So series compensator, injected voltage, and shunt compensator, injected current. So this D-STATCOM injects current and it compensates the load harmonics, load power factor, load unbalance. And this DVR injects the voltage, which compensates the voltage. I mean voltage harmonics, voltage sag, voltage swell, etc. This series compensator is on left side and shunt compensator is on right side. Or it may be like this. You may have shunt compensator on left side and series compensator on right side. Both possibilities are there. And then this is your load voltage and this is the load. So this is DVR and this is D-STATCOM. Practically it is realized like this. Let me show you actual practical realization. Practically it is realized like this. Let me show you full diagram. This is as usual source voltage Vs. This is a distribution transformer. This is bus number 1 जहाँ पे आपका load connected है, load. And then this is your feeder. Feeder carries the feeder current or source current IS. ये point of common coupling है VT. और यहाँ पे आप क्या करते हैं? What you do is you have DVR like this through injection transformer. Let me first of all complete the power circuit or schematic diagram, and then I will try to explain it. Okay, it is this. This is the injected voltage VF, and you have another voltage, three-phase voltage source inverter, which is D-STATCOM, which injects the filter current IF. और ये आपकी लोड वोल्टेज VL है और यहाँ पे आपका डिस्टॉर्टिंग लोड है जिसकी कंपनसेशन चाहिए, सेंसिटिव लोड. तो इसमें कॉमन DC बस हम रखते हैं. इंस्टेड ऑफ हैविंग सेपरेट DC बस फॉर दिस इन्वर्टर एंड सेपरेट DC बस ऑफ दिस इन्वर्टर, वी हैव अ कॉमन DC बस. So what is this? It injects the voltage into the system. So this is DVR. And what is this? It injects, this is series connected. You can see ये ट्रांसफार्मर की सेकेंडरी सीरीज है और यहाँ ये शंट कनेक्टेड है. This is series connected compensator. It injects voltage in series with the bus. It's DVR. And this is shunt connected compensator. It injects the current, not voltage. And this is D-STATCOM. और इन दोनों की कॉम्बिनेशन जो है ये, this is combination of DVR and D-STATCOM. It is called UPQC, Unified Power Quality Conditioner. So these are three different types of compensating type. This as far as this D-STATCOM is concerned, it compensates the load, it balances the load, it takes care of load balance, load unbalancing, it compensates the harmonics in the load current, and it also supplies the reactive power demanded by the load, thus compensating the load and making the source current purely sinusoidal, balanced and in phase with the voltage. So it addresses the current related power quality problem. And this DVR injects the voltage. This voltage compensates the voltage distortion in the voltage, supply voltage. It takes care of voltage sags, voltage swells, and hence it addresses the voltage related power quality problems. It may happen that this load is polluting load and simultaneously source has dips, it has sags, swells and distortions also. So in that case, you need both type of compensations. You need load compensation as well as voltage compensation. So you need both DVR as well as D-STATCOM. So we use a single custom power device which is called Unified Power Quality Conditioner, UPQC, which is actually a combination of DVR and D-STATCOM, with DVR compensating for voltage related power quality problems and D-STATCOM compensating for current related power quality problems. So these three type of custom power devices, which are load compensation type or compensating type power, custom power devices, inshallah in future lectures we have to discuss them in details. Most of our discussions will be around these. To end my today's lecture now, let me discuss something very interesting with you. It's a new concept. It's called custom power park. Custom power park, CPP. Custom power park. Custom power park is a concept, or it is a technology in which a very high quality of power is supplied to certain category of customers, like a very sensitive load, like industrial load, hospital load, etc. So let me first of all draw the schematic diagram of a custom power park, and then I will explain. This is substation 1. Circuit breaker. Then I have another substation. Substation 2. Circuit breaker. And we have solid state transfer switch, SSTS. And now something very interesting is there. We have a circuit breaker here. We have two lines. This is A. This is AA. This is standby generator. Standby generator. This is DVR, injected voltage VF. Injected current IF. This is D STATCOM. And finally, we have another type of customer here, AAA. AAA. This is Custom Power Park, CPP. This is, okay. Now we have two feeders. We have here feeder 1 and we have feeder 2. This is solid state transfer switch. Now in this custom power park, the power has three grades: grade A power, grade B, grade AA, and grade AAA, AAA, AAA. We have three types of customers: grade A customer, grade AA customer, and grade AAA customer. Or we have three types of power depending upon the quality of power: grade A power, grade AA power, and grade AAA power. Now this custom power park comprises of two substations, two feeders coming from two different substations. This is feeder 1, this is feeder 2. Then we have a solid state transfer switch, SSTS, which we have already discussed. Then we have these crosses, these boxes are all circuit breakers. Then we have a standby generator here. Then we have these custom power devices also, like DVR and D STATCOM. Okay. Now let us take grade A power or grade A customer. Grade A customer is supplied generally from feeder 1. Okay. It's supplied from feeder 1. In that case, this circuit breaker is on. Okay. It is supplied from feeder 1. What type of power supply it gets? It gets almost sinusoidal power, because this D STATCOM takes, if there is a polluting load somewhere here, that polluting load would have caused polluting voltage distortions supplied to the grade A customer. But this D STATCOM compensates for harmonics in the load of AAA customer, and hence it makes the currents in the feeder sinusoidal. So the power is at very high quality. Sinusoidal currents, sinusoidal voltages are supplied to grade A customer. In the event of a voltage sag or voltage swell or a fault on this feeder, let us suppose this feeder goes out of service, there is a fault, then immediately second feeder will be connected through solid state transfer switch. What will solid state transfer switch do? It will start supplying grade A customer from feeder 2. This may be preferred feeder, this may be alternate feeder. It starts supplying the customer from feeder 2. So therefore this customer gets uninterrupted power supply and good quality of power supply, sinusoidal voltages. But what will happen if there is fault on both the feeders? This feeder goes, this feeder also goes. In that case, this grade A customer will not get any power. There will be complete disruption of power. Come to grade AA customer. Grade A customer will have all the facilities that grade A customer has. In addition, grade AA customer will get power from standby generator in case there is a failure of both the feeders. Let me explain it. Generally, when feeder 1 is operating, there is no fault. So AA customer will get power from feeder 1. In case feeder 1 develops some fault, this solid state transfer switch will start drawing power from feeder 2 and grade AA customer will get power. And it will get purely sinusoidal voltage because of this D-STATCOM. Just like, so that means all the facilities which are provided to grade A customer, those will be provided to grade AA customer also. But grade A customer, in case of grade A customer, there was a problem that if the feeder 1 fails, feeder 2 also fails, then there was power failure to grade A customer. It was not getting power. That is not the case with grade AA customer. So for example, there is fault on feeder 1, इसका circuit breaker trip हो गया, feeder 2 में भी incidentally fault हो गया और इसका feeder circuit breaker भी trip हो गया. So no power is coming from this feeder, no power is coming from this feeder. But in that case, what will happen? This standby generator, which may be a diesel or gas generator, yes, start ho jayega. It may take 10 to 20 seconds to start. And after 20 seconds, this AA grade customer will start getting supply. तो इसको power disruption 10 से 20 सेकंड के लिए सहनी पड़ेगी, and then it will get continuous supply from this standby generator till the fault in any of these feeders is rectified. इनमें से सबसे हायर ग्रेड का फीडर कस्टमर AAA ग्रेड का कस्टमर है. ग्रेड AAA कस्टमर जो है, इट मे बी अ हाईली सेंसिटिव लोड, लाइक हॉस्पिटल का ऑपरेशन थिएटर, हॉस्पिटल में जो लाइफ सपोर्ट सिस्टम है, that may be supplied by this type of power, grade AAA power, and maybe some processing industry like semiconductor manufacturing industry is supplied through this, by this power, and food processing industry is also some, जहाँ पे voltage sag नहीं होना चाहिए, voltage swell नहीं होना चाहिए, flicker नहीं होना चाहिए, जहाँ पे purely sinusoidal voltage मिलनी चाहिए और uninterrupted power supply मिलनी चाहिए. Let us see how this grade AAA customer gets all these qualities, all these specifications. Grade AAA customer gets all the facilities that grade AA customer gets plus some additional facilities. If feeder 1 normally operate kar raha hai, there is no fault, this grade AA customer will get power from feeder 1. Agar feeder 1 mein fault ho gaya, immediately this SSTS will start supplying power from feeder 2. अगर दोनों फीडर्स में फॉल्ट आ गया तो ये जनरेटर चालू हो जाएगा, लेकिन इसको 10 से 20 सेकंड लगेंगे चालू होने में. उस वक्त तक अगर यहाँ पे एक बैटरी स्टोरेज आपने DVR में रखी है, दिस बैटरी विल स्टार्ट सप्लाइंग पावर टू द कस्टमर 10 से 20 सेकंड तक. और इसमें चूंकि हाई कैपेसिटी बैटरी आपको लगानी है जो 20 सेकंड तक इस इंडस्ट्री या इस सेंसिटिव लोड को पावर सप्लाई करे, जब तक ये जनरेटर चालू हो जाता है. और जब ये स्टैंड बाय जनरेटर चालू हो जाता है, प्रॉब्लम इज सॉल्व्ड. सो देयर इज नो इंटरप्शन ऑफ पावर टू ग्रेड AA कस्टमर. एंड इफ देयर आर वोल्टेज सैग्स, स्वेल्स और वोल्टेज हार्मोनिक्स, दोज विल बी टेकन केयर ऑफ बाय DVR. और अगर लोड में यहाँ डिस्टॉर्शन है, हार्मोनिक्स है, अनबैलेंस है, दैट विल बी टेकन केयर ऑफ D-STATCOM. So AA customer will get all highest quality of power. You will get purely sinusoidal voltage, uninterrupted power, no voltage sag, no voltage swell, pure sinusoidal voltage, uninterrupted power, highly reliable and high quality power. अब ग्रेड AA एक हॉस्पिटल में दोनों सप्लाई. अब ग्रेड A पावर किसको मिलना चाहिए? जनरली रेजिडेंशियल लोड को या मे बी कमर्शियल लोड, शॉपिंग मॉल, दे मे डिमांड ग्रेड A पावर. फीडर 1 नॉर्मली सप्लाई करेगा और अगर फीडर 1 ब्रेक डाउन हो गया, फीडर 2 से पावर आएगा. सो शॉपिंग मॉल्स, शॉपिंग कॉम्प्लेक्सेस एटसेट्रा. AA ग्रेड कस्टमर कौन सा कस्टमर हुआ? से हॉस्पिटल. हॉस्पिटल में अब ऑफिस अलग होता है, पैथोलॉजी लैब्स अलग होती है और ऑपरेशन थिएटर अलग होता है। ऑपरेशन थिएटर और लाइफ सपोर्ट सिस्टम को आपको अनइंटरप्टेड पावर चाहिए, तो वो ग्रेड ए पावर उसको मिलेगा। लेकिन हॉस्पिटल में जो ऑफिस वगैरह है, एडमिनिस्ट्रेशन ब्लॉक है और पैथोलॉजी लैब्स है, उनके लिए आपको ए ग्रेड की सप्लाई ज़रूरत नहीं है, उनके लिए ग्रेड ए पावर भी काफ़ी है। ग्रेड ए पावर में फीडर 1 से पावर आएगा, अगर फीडर 1 फेल हो गया तो फीडर 2 से पावर आएगा, अगर फीडर 2 भी फेल हो गया तो 20 सेकंड के बाद जब ये स्टैंड बाई जनरेटर चालू हो जाएगा तो ये सप्लाई करेगा। लेकिन हॉस्पिटल में जो ऑपरेशन थिएटर है, लाइफ सपोर्ट सिस्टम है, वेंटिलेटर्स हैं, ऑपरेशन थिएटर इक्विपमेंट है, उसको ग्रेड ए पावर मिलेगा। तो दैट मीन्स हॉस्पिटल विल गेट बोथ ग्रेड्स ऑफ पावर, ए ग्रेड एंड ए ग्रेड। ए ग्रेड will be supplied to offices, administration block, pathology labs, and A grade power will be supplied to operation theaters, life support systems. So this is the custom power park. So therefore, custom power park supplies a high quality, highest quality to grade A customer, followed by grade A and followed by grade A. Even the basic customer, which is grade A, that also gets better power supply than normal customer. But this custom power park tariff यहाँ high होंगे. I mean the bill that the cost per unit of energy for grade A will be higher than normal customer. For grade A, the cost of energy will be even higher, and the cost of energy per unit will be highest for grade A customer. This is the concept of custom power park, or Europe में already this concept of custom power park is in vogue. It's in operation. I hope in India also and in other South Asian countries also, in future, as the widespread use of custom power devices is there, we can say we are using custom power devices here also. So for reliable, uninterrupted, high quality power supply, this custom power park concept can be used in these countries also. So with this, I will end my today's lecture. In today's lecture, I have discussed an overview of various types of custom power devices. We have defined the term custom power and custom power devices. We have given I have given you the utility customer interface concept, why custom power devices are needed. We have categorized or classified the custom power devices into two categories. Number one, network configuring type, and number two, compensating type. Network configuring type of custom power devices are of three types: CL, that is solid state current limiter, SSB, solid state breaker, and SSTS, solid state transfer switch. And compensating type custom power devices are also of three types, where load compensation is required, that is DSTATCOM, which is a shunt connected custom power device, where voltage compensation is required, that is series connected custom power device, or DVR, and a combination of the two, shunt and series compensators, that is unified power quality conditioner, UPQC. Although in this custom power device, in this custom power park, I have shown DVR and DSTATCOM separately, but you can replace them by UPQC. This can be a UPQC also. In case of a UPQC, you will have a common DC bus. It can be UPQC also. Okay. And finally, I told you that DSTATCOM, which is a shunt connected custom power device, it takes care of current related power quality problems. It compensates the load. And DVR, which is a series connected custom power device, it compensates for voltage related power quality problems. And UPQC, which is a combination of the two, it takes care of both voltage related as well as current related power quality problems. And finally, I gave you an idea about custom power park. And in custom power park, we have three grades of power: grade A, grade AA, and grade AAA. Grade A may be residential, some residential customers, shopping complexes, offices. AA may be, hospitals, parts of hospitals, some sensitive loads, and AAA, hospitals, operation theaters, life support systems, etc. A hospital may have both grades of power, AA as well as AAA. AA will be given to offices, administrative block, and pathology labs, and AAA to operation theaters and life support systems. AAA grade power is also given to industrial processes like semiconductor manufacturing unit and this food processing industry, etc. With this, I will end my today's lecture. Wishing you all the best. Stay connected with me. In case of any doubts, any clarifications, please ask me. Thank you.